So this will be the fourth lecture out of chapter 18, so this will be the last lecture in chapter 18. So we'll just look at a few more reactions of aldehydes and ketones. So in this lecture we'll just look at how aldehydes and ketones oxidize. So if you remember back in the alcohol chapter, we talked about aldehydes being susceptible to oxidation. So they can be easily oxidized. They can be oxidized by air, oxygen in the air. So if you have a bottle of aldehyde in lab and it's been open and closed over the course of several weeks or months or years, then you'll probably find some carboxylic acid in that flask because some of the aldehyde has been oxidized to carboxylic acid. So basically any strong oxidizing agent will oxidize the aldehyde to a carboxylic acid. So just take the hydrogen, write OH there instead, you got the carboxylic acid, right? So if you remember your oxidizing agents from back in chapter 11, so if you take an aldehyde with sodium dichromate, for example, and water and acid, so water reacts to make the hydrate, and then if we oxidize, so lose H and H across the CO bond, you have a carboxylic acid. So we won't go through the mechanism for these. We talked about them a little bit back in chapter 11. So just to remind you of the oxidizing agents, so KMnO4 would oxidize the aldehyde to carboxylic acid, right? Chromic acid, H2CrO4, sodium dichromate. This one's a new one. You can use just Br2 to oxidize an aldehyde. This one's new as well. This one's what's known as the tolerance test. If you take silver, silver ammonia complex with sodium hydroxide, then that will oxidize the aldehyde to carboxylic acid. So this one used to be used, or it still is used, if you think you have an aldehyde, then one way to test it and see if you had an aldehyde without doing any spectroscopy at all, because spectroscopy, you get to have a really expensive instrument to do that. Here you just need some pretty cheap chemicals. If you do this tolerance test, well, this is silver 1 plus 1 oxidation. So if the alcohol is being oxidized, then something's being reduced. So what's being reduced is silver. If you remember, reduction is the gain of electrons. So if silver gains an electron, if silver plus 1 gains an electron, it becomes silver 0. How can you tell that silver 0 is being formed? Because you see a mirror being formed in your reaction flask. And so that would be an indicator that you had a aldehyde which is being oxidized to a carboxylic acid. Right, or you could use silver oxide and base hydroxide will oxidize aldehyde to carboxylic acid as well. So if you remember back in chapter 11, we talked about the oxidation of primary alcohols. They can be oxidized to aldehydes, but if you want to stop at the aldehyde, then you have to use a weak or a mild oxidizing agent. And if you remember what those reagents are, PCC, PDC, we talked about the Swarin oxidation or DMP, the desmartin pyridine. So those will take a primary alcohol and stop it at the aldehyde. If you use a stronger oxidizing agent, then the primary alcohol would go to the aldehyde, and then the aldehyde would oxidize further to the carboxylic acid. Right, with any of these oxidizing agents. And of course there are others, those are just the ones that you have to know. Okay, so ketones can be oxidized. So ketones will oxidize to, you can oxidize them to esters. So you can do what's known as a Baeyer-Villiger oxidation. So this is the way you do it. You take a ketone with a peroxy acid. So this is a peroxy acid. You have a C double bond O, OOH is a peroxy acid. So this will basically insert an oxygen. So it'll insert that oxygen into one of the carbon-oxygen bonds that's flanking the C double bond O. So you can insert it there or you can insert it there, but the way that it works is you get preferential insertion between C double bond O and the more substituted carbon, so this is the one that's preferred. So that's the pathway that's faster. So how does this work? So the basic mechanism, so let's take a lone pair on this oxygen, make a bond to carbon-oxygen double bond, since that carbon's partial positive and oxygen's partial negative. Then we're going to lose a hydrogen from this oxygen. And now what happens is a rearrangement. So we're going to remake the carbon-oxygen double bond, and then we're going to get a alkyl group migration. So this is going to migrate to oxygen, and then that's going to kick this off. So then that gives you the ester. And then that gives you the conjugate base of benzoic acid, which will pick up that proton that was lost in the previous step. And so you get benzoic acid side product. But so basically you just have to learn the recipe again. If you see a ketone with a peroxy acid, then just take that oxygen and stick it between the carbon-oxygen double bond and the more substituted carbon that's attached to it. Okay, so last example here. So we have a ketone, we have a peroxy acid. So this oxygen needs to go either between these two carbons or between those two carbons. All right, so where is it going to go? Well, this carbon is secondary and this carbon is primary, so it's going to go to the secondary one. So you would make that. So you went from a 6-membered ring, 1, 2, 3, 4, 5, 6, 7, yeah, to a 7-membered ring. So you did a ring expansion in this case. And so you made a cyclic ester. Since you started with a cyclic ketone, and if you remember, cyclic esters are called lactones. Okay, so just to predict a few products, so if we took this aldehyde with chromic acid, then oxidize the carboxylic acid, right? Or if you took this primary alcohol and secondary alcohol, so that would oxidize to the aldehyde and ketone. But if you use the KMNO4, so this is weak or mild and this is strong, then you still oxidize the secondary alcohol to the ketone, but the primary alcohol would go to the aldehyde, which would then oxidize to the carboxylic acid. Okay, and lastly in this chapter, just to remind you a little bit about the spectroscopy of aldehydes and ketones. So in terms of IR, what's significant is, right, you see a CH stretch for the hydrogen attached to aldehyde, and you see the C double bond O stretch. And then where are those at? So this is about 2700 to 2800, and the C double bond O is around 1700. And if you have a ketone instead, then you don't have the CH stretch for the aldehyde anymore. You just have the C. Of course, you would see these CH stretches as well, right? But those are at a different spot. So those are around 2900. So the point is, with the ketone is missing the 2700 to 2800 signal, so you can differentiate between an aldehyde and a ketone that way. So this would just have the C double bond O stretch around 1710, 1720 centimeters. And of course you would still have the CH stretches for this around 2900, but that's going to be the same in the aldehyde as well. And if the C double bond O is in conjugation, right, these are conjugated double bonds, then that shifts them to a shorter wave number. So then those C double bond O now would be around 1680 to 1690 centimeter. So you wouldn't want to confuse that. Well, the C double bond C is around 1650 centimeter, right? Okay, and then in terms of proton NMR, so what's most characteristic is for aldehydes is that signal, right? If you remember where that hydrogen is at. If you see a signal around 9 to 11 ppm, that's an indicator of an aldehyde. And then hydrogens next to C double bond O's are around 2 ppm. So if it was a ketone, you would see a signal there, or an aldehyde, you would see a signal there, so long as there's a hydrogen on that carbon. But for a ketone, you would not have that signal from 9 to 11, but you would for aldehyde. And then in carbon-13 NMR, the most characteristic signal would be the C double bond O carbon. If you remember where that is at, that is between 200 to 220 ppm typically. Okay, that's it for chapter 18.